modeling technique to construct a graphical representation to show the structure of the random variables. We showed many applications. These applications, these applications, sometimes they're easy. They're just too simplified, because many cases you don't have control. You simply observe what happened. Then you have some hidden states. So you want to infer what happens, or what's the sequence of hidden states, or what's the most likely observation, or what's the most likely sequence, etc. So this problem sometimes is simplified. It's a simplified question. But in a practical use case, typically for this so-called online estimation means you are given some observations and you can actively affect to the system. This is called online estimation. Right? Online estimation. We have many applications. A typical application will be a SLAM problem, right? Localization and mapping. We encountered SLAM in the second week, or partially the first week as well. But in today's lecture, we want to look deep into how can we really apply those beliefs, into some formats that we can really do the computation. Right? We can really compute each of the components. And what's the inherent connections between the among the prior, likelihood, posterior, and also extend that to some applications of common filter. If you know about the common filter already, it's good. If you don't know, we will quickly wrap up what is common filter as well. So that's the things we will talk about today. Also a little bit next week. So the overall topic is called online estimation. It's called online estimation. We introduce two solutions. One is a Markov localization. Second one, typically we call that a common filter localization, but it doesn't matter. What matters is the inherent structural representation. Okay, the problem is, again, we want to revisit this localization problem. Okay, if we consider mobile robots moving in a known environment, that means you have the map already. Right? If you have the map already, then it starts to move. Say you start to move from a previously known location, and then it can keep tracking its location using the wheel odometry. Right? What is the wheel odometry? That means you put some encoders. Right? Some encoders will be on the wheel, so you can measure how much the wheel turns. Right? How much each wheel turns. So after a certain movement of the robot, we'll get quite uncertain about its position, right? Because of what? The encoder will make mistakes, right? Make mistakes. It doesn't make mistakes in counting the ticks, but make mistakes when you have a slippery floor. So there are slippage between the wheel and the ground. Okay, and sometimes for this caster wheel structure, if you have two caster wheel and two driven wheel, and on an uneven floor, some of these driving wheels they may be floated, right? Maybe floated. So because 3 points already define the plane, right? So if there's a hole here on the ground, and then this guy will spin without any actual action of the robot. Okay, so the robot will get uncertain. And the next step is observations. Will lead to estimation of the robot position. Then we can fuse the odometry, odometric estimation, to the best possible update. What is the best possible? The best possible, another way to say it is optimal. Right? To an optimal update of the actual robot position. Right? What is optimal? Optimal means you cannot do better. Right? You cannot do better, so it's optimal. Optimal doesn't mean zero error. Right? Doesn't mean that. Just you cannot do better. This is already optimal. Okay. That's a problem, right? So compare with the example of the first week. Now we are getting more serious about this definition, right? More serious about this definition. So we want to like using a magnifier to see in depth what is localization and what is actually happening. A robot moving in a map, and it will accumulate errors with the odometer, and then some motivations will help you to have optimal estimation. Right? Sorry, that's what happens in this localization process. Okay. In a classical representation, so what is localization? Localization means we have an environment. So let's say this environment is 3 pillars. Right? So number 1, number 2, number 3. Right? We have 3 pillars. And on the robots, you have a sensor. You see the small sensor here. You have this sensor. This sensor cannot do much. Right? It can only generate observation Z. This observation Z, you see, it's in lowercase. That means I see a pillar. Okay, I see a pillar. Okay, so that's your observation. Right? That's your observation. Then the localization process is clear. So starting from the initial states, the robots you put somewhere in the environment, but is not told its location. You don't know where you are. And then you query its sensor to find it's next to a pillar because you have this observation Z. Right? You have this observation Z. What's that? Right? What's that? So the problem you try to solve is actually what? Is I want to know my location, the state, given the Z and Y. This is a real problem we want to solve. Right? This is a real problem we want to solve, but only by knowing a pillar is not good enough, right? So that's all. From this example, we also show, we also see the causal reasoning is much easier than the diagnostic reasoning. Okay? So we use a causal reasoning. That means we build a likelihood model. Right? This is a likelihood. What is likelihood? Likelihood said, if I know the map, I know the map, and I know my location X. Okay, I know the map and I know the location X. What's the probability of Z? What's the probability of Z? What is that? That is I see a pillar. That probability is a likelihood shown like this. Right? This is the probability. Okay, this is natural. You have 3 pillars in the environment, so the P of Z given X and M is this guy. Okay, is this guy. Then the robots move 1 meter forward. So before the robot moves that, what do you want to do? Having a likelihood is not good enough, right? Having likelihood is not good enough. You want to do a posterior, like this one is a posterior, should be a prior times a likelihood, right? A likelihood. So what is a prior? We said that the robot is not told its location. The prior is nothing else than uniform, right? You cannot do better than uniform. So the prior, this prior times the likelihood, this is a likelihood, what do you get? Then after normalization, right, you need to consider the normalization. Divide by the evidence, right, is actually the normalization. By normalization, the uniform is not taking any effect, right? So finally, this this posterior will be equal, right? It's identical to this likelihood, right? Identical to this likelihood. We use the posterior, this posterior, as a prior for the next cycle, right? We name it as a belief. So you know what is belief, right? We already discussed what is belief. Belief is a posterior, x given z and n. Right? So this guy is identical to the likelihood, right? This is a new belief. After the new belief, getting the new belief, there is a one step missing, is we moved 1 meter forward, right? We moved from the previous location 1 meter forward. And then what? Then the belief should shift to the right, right? The shift 1 meter to the right. The three bumps, you see these three peaks, the position of these peaks will all move, right? We all move 1 meter forward. And another thing is because you have odometry, and sometimes this odometry introduces additional error. This additional error causes what? Causes you have further uncertainty. You have further uncertainty. So all these peaks, right? The height of the peak will drop. Right? They will drop. They move to the right, and then the height of the peak will drop. Okay, that's what you observe. So mathematically, what we had, right? Well, mathematically, we have previously we have a belief. This belief is exactly the shape as this one, right? Exactly the shape of the likelihood, because likelihood times the uniform, you normalize it, is still the shape of likelihood. It's the likelihood is the same shape as the posterior. Is the belief, right? So belief has the same shape as the likelihood, and then we move 1 meter forward. Move 1 meter forward, and the height of the peak will drop, and they move 1 meter to the right. This process is nothing else than what? It's a convolution. Right? It's convolved with Gaussian noise if the motion model is Gaussian. So later we will discuss, right? So robot move 1 meter forward. To account for the inherent noise in robot motion, the new belief is smoother. Smoother means the peaks will drop, right? Okay, after that, you have the robot will query its sensor again. Query the sensor again, and again it has a Z. What is Z? Z means I see a pillar. Z means I see a pillar. Then what? This guy is identical as this one. Right? No matter the shape or the physical meaning, right? They are exactly the same. It's all both PZ given X and N. Okay. This likelihood will not change. The likelihood not changing. But the actual position of the robot changes, right? So it changes. It's moved 1 meter forward. The shape of the likelihood will not change. So the magic happens in the last step, right? Here is the magical. Why this is the magical? Because we can use the likelihood, this likelihood, multiply with the previous belief. What's that? Previous belief. This is a prior, right? This is a prior. Multiply a likelihood. You get what? You get a posterior, right? This posterior will be this shape. Okay, this process is easy. So let's erase everything. First question. First question. How could you multiply? How could you multiply the A and the B? How do you do this multiplication? How can you multiply? Particle filter? No. Particle filter is a filter. It's a different concept. So what I'm asking is very easy, right? So we said that you have, okay, we have all the concepts, right? Fancy concepts. This is a prior, right? This guy is a prior. This guy is a likelihood. Okay. Bayes' rule tells that if you multiply prior with the likelihood, you get posterior, right? The concept is too easy, right? So the question is, this multiplication, how could you do it? How? How do you multiply? Discretize, good. This is the correct direction, right? This what? If you have this is a vector 1, this is a vector 2, is what? It's a dot product, right? Right? Pointwise. It's a pointwise multiplication, right? That means for the first position, multiply with the first position, you will get this guy, right? Get this guy. And this one, multiply with this one, I will get the peak, right? This one, multiply this guy, I will get this one, right? Okay, this is clear. So this one multiply with the peak, I will get another peak. So this is clear, right? It's a pointwise multiplication. And this is important, right? This is important. Okay, again, pointwise. So why this is important? Because if you apply this model to mobile robots in the 2D, right? Here is just a toy example. If you move that in 2D, then you can tessellate the environment into grid, right? And then you can do the pointwise multiplication over the grid. Okay, pointwise multiplication over the grid. Okay, this is clear. So finally, this is belief. We'll combine the information and the previous belief. So quickly summarize. Initially, you don't know what happened. So this is a uniform. And you see a pillar Z. Z says you say you have a pillar. You have this likelihood, right? And then this likelihood is the same shape as a posterior. So you use the posterior as a prior, then you move to 1 meter forward, then it's getting smoother. And this guy is a posterior. Also, it serves as a prior. Also, this is a prior for the next cycle, right? Also, is a prior for the next cycle. And then you have, again, a likelihood, right? Multiply the prior with the likelihood, you get a posterior. Also, it's known as a belief, right? So this is simple, very simple. And what is important is the result of localization is what? It's not a point estimation. Right? So the data coming from the robot sensor are affected by the measurement error. You can only compute the probability that the robot's in a given configuration. Right? It's not a point estimation. You only have a probability or distribution. The key idea in probabilistic robotics is to represent this uncertainty. Instead of using a single best estimate, finally you have a probability distribution. Right? We don't want a single best estimate. It's not good enough. Not helpful because you have so much uncertainty. That's why we use a probability distribution. This is called a belief. This is called a belief. And I know about the equation of belief already, right? Previously in the lecture. So belief is what? Belief of x. Belief of x is what? Is the post area of xt given what? Given all the previous controls and the previous observations, right? This is the belief. Of course, if you want a point estimation, it's easy, right? I just check, okay, I want this point. Then the robot location should be at as this star location. But you have the general distribution of the probability all across the space. Good. Any questions so far? No? No questions? Good. Then there are certain probability distribution, right? So if you consider robots constrained to move along a straight line, then the problem is one-dimensional. Like the robot can be here, can be here, can be there. Right? You have different possibilities, right? Then the PDF, probability density estimate function. Right? This is the density function. Probability density function. PDF will reveal the real configuration. The real configuration. For example, if it's equally distributed, quite equal, then this is uniform, right? Uniform. That means what? Means the information is zero. Right? You don't have any information about the position. The best you can do is just grant a uniform. Just grant a uniform. In whatever case, the integral of PDF goes to 1. Right? Okay. Second case is most of the cases you get a multinomial distribution. That means the robot can be around A or around B. Okay, around A or around B. And if you want to get a sample from this distribution, the sample may look like this. Right? May look like this. So strokes like they are the possible locations. So this is a multinomial distribution. It can also be a Dirac distribution. So that means you're 100% sure at the position A. So this function says that only when x minus a equal to 0, and then you have infinity, right? Otherwise, it's 0. That means you're very sure about the location. Okay, another case is a Gaussian, just a Gaussian. The Gaussian is the shape of a bell. It's also an exponential family. Why this is important? Because if it's an exponential family, it's easier for the derivation, right? It's easier to compute the differential. Easier to differentiate, right? It's an exponential family. So Gaussian distribution, everybody know about that, right? So you have a mean at the center of the assumptions, and you have sigma shows the uncertainty. It's a variance. Variance. Also, that's the uncertainty, right? It represents the uncertainty. This is the Gaussian distribution, right? This is the Gaussian distribution. Next. Okay, if we combine what we know, what we have known from the 1D case and all these distributions, okay? If we combine this, and what happens what will happen in 2D, right? What will happen in 2D? Consider you have a mobile robot moving in a known environment. You see here is a corridor. Sorry, this is a door. This is the door. And then this is a free motion area. This is a free motion area. Start to move, and then the distribution of the uncertainty will change, right? Will change. It will change from a point estimation to a two-dimensional Gaussian. This is the shape of the 2D Gaussian. 2D Gaussian. Interestingly, this Gaussian shape in a real robotic application, it always looks like this. Okay, this is the front of the robot. It's a draw robot. This is the top view of a real robot. This uncertainty always grow like this. Why? Do you know why? At least it shows the uncertainty appear differently, right? It's a lateral direction. That means along the motion of the robot. Let's say, give it a name. Right? This is the X. This is a Y. This is Y, and Z is pointing down, right? If this is the X, this is the Y, then the uncertainty in X direction will grow slowly, a little bit slower than the sigma Y, right? Than sigma Y. This is caused by what? Caused by the motion of the wheels, right? Because this uncertainty purely is on the motion of the wheel. And if you have these two wheels moving to one direction, often the case is one wheel may be stuck or floated, and then the uncertainty in the y direction, in the particular direction, will be much bigger, right? Much bigger, because once the left wheel is blocked, and then the robot will turn left, right? Will turn left. But you think the robot is moving straightly forward, but actually it will turn left if the left wheel is blocked. So you get higher uncertainty in the x direction, in y direction than the x direction. Okay, then this uncertainty will grow, right? This is called the motion update. Right? This is called the motion update. And due to this odometry uncertainty, after certain movements, the robot will be very uncertain about his position. Right? Will be very uncertain about his position. Finally, this distribution will become what? You don't know where you are anymore, then this will become a uniform, right? It will become uniform. So like a Gaussian, and then you have a flatter Gaussian, then even flatter Gaussian. Finally, this is a uniform, right? Finally, this is a uniform. Well, To keep the position uncertainty from growing unboundedly, and then the robot must localize itself related to the map. To localize it, we need some exteroceptive sensors. Exteroceptive sensor means what? Means you can observe the environment right outside yourself, like ultrasonic lidar vision, right? Or vision. So in the sensor frame, this is not a world frame, right? This guy is a world frame. Okay, this is a sensor frame, or you call this is the robot frame. This is a robot frame. In this frame, now you observe the door, right? Observe opening, right? Observe this opening, and this observation can be a Z, right? So you want some explanation. So you have Z, you have M. So where I am, you want the P of X given Z and M. So exactly the same equation as the 1D case. What do? You need to multiply this likelihood with this guy. This guy is a prior. Okay, you need to multiply the yellow part. And this yellow part with this guy. Okay, on the right side, this is likelihood, and then left part is the prior. Okay, this is clear. How do you do the multiplication? As we said, you need to do a pointwise product, or a pointwise product. How do you do that? How do you do that? You know, this is a space you care, right? This is a space you care. So there must be this guy must be a reference frame. In the world reference frame, you have uncertainty, right? So you need to have a dot product of the red Gaussian with this yellow Gaussian, right? With this yellow Gaussian. So you need to find the product of the two Gaussian distribution. Okay, what will happen? If you have a product of these two Gaussians, then what will happen? The result will be a Gaussian distribution multiplied with a Gaussian distribution. You will have what? A Gaussian times Gaussian. You get what? Get again a Gaussian, right? Get again a Gaussian distribution. I will discuss the proof if you have time next time. So you have a Gaussian distribution N1 multiply with a Gaussian distribution N2. What? That will give you a Gaussian distribution of N3. What do you get? What do you get? Should assume sensors are unbiased. Yeah, we don't care about the sensor modeling yet, right? So you can assume that it's unbiased. You can assume that it's unbiased. So we're not discussing the characteristic of a sensor yet. Right? So far, even the motion model is perfect, right? So you see the prior here is a Gaussian. Actually, the prior is not a Gaussian. It cannot be a Gaussian. It's just some shape that looks like a Gaussian. So this, but if we following this assumption, this prior is Gaussian. This prior is a Gaussian. So N1 times N2, you will have a new Gaussian, which is N3. This N3, for example, you have the hyperparameters as a mu3 and the sigma 3. What do you get? You will have the mu3, mu1 times the mu2, right? And the sigma 3, what about sigma? Sigma 3 is what? Sigma 3 is smaller than sigma 1, and it's smaller than sigma 2. I want you to remember this. Okay. There is an easy proof, right? That I can list a PDF file to show the complete proof. Yeah, why is this smaller? Because there is a proof, right? There is a proof. So this sigma 3 is smaller than sigma 1, and it's smaller than sigma 2. Okay? It's a good question, right? Why is it smaller? So you can find the proof. Later I can give you. So remember this as a conclusion, okay? A Gaussian times a Gaussian gives you a new Gaussian. And for this new Gaussian, the uncertainty is smaller than any of the multiplier. Okay. This is very important. Yeah, in a more restricted region. Yeah, smaller region, right? Smaller region. This is very important. We use this. This is why common filter can work, right? This is why common filter can work. Also, this is why, let's say, if you use a GMM estimator, the MLE can finally converge. This is why. Right? This is exactly the reason. Sigma 3 will be smaller than sigma 1, and it's smaller than sigma 2. In the context of 1D case, let's say, if you have sigma 1 in red, there is sigma 2 like this one in blue, and then the sigma 3 in green will be something like this, right? This is the 3. Sigma 3 is smaller than sigma 1 and smaller than sigma 2. Okay, firstly, remember this as a conclusion, and I will give you a proof, right? I will give you a proof. So the result is like this. You can see the dimension. This dimension is smaller than this guy. Also, this is smaller than this guy. This is perfect, right? This is perfect. And the position of the location will be in the middle between the prior and your restricted. For example, the red dots is it's here. The cross is just in between. The new mean is just in between. Okay, that's what happened in 2D. Let's have a rest. Take a 5 minutes rest. Okay, have a quick break. Okay. Sorry for the delay. Because I took some time. It took some time to give you the proof. So I try to get the complete proof from somewhere else. During the break, I wrote these equations. These equations. Because I want to show the product of two unary Gaussian. You have again it's a Gaussian. Again it's a Gaussian, and then the sigma is smaller than any of the multipliers. This is a quick proof. That means there is a scaling factor missing, but that scaling is missing on the values. It's not on the variance itself. So if you have a fx and a gx defined with the mean at mu f or sigma f, and then the product fgx is this guy, right? So 2 pi times 2 pi square root, you get 2 pi, and then finally you get an interesting part, right? This part. So that's a copy paste from the previous one. x minus mu f squared over 2 sigma f squared plus the g part. And if we call this part, denoted part by alpha, and then the alpha can be expanded as this one, right? Expanded by this one, and then both denominator and denominator can be divided by this part, sigma f plus sigma g, the coefficient of x squared. And then you get what? You get, again, a quadratic form. This is important. You can see this is the quadratic form of x minus something square over 2 times another something, right? So that means this structure is exactly the same format as a Gaussian distribution, right? So what is missing is just what is the mean and what is the variance. So, but we can estimate the mean and the variance. Consider this is x minus 2 times of something x, then plus something square. So you see here, it's not exactly the same. Right? There is a small scaling difference, but as long as it's a quadratic form, what does it affect? It only affects the bias. Okay, they only affect the bias. Maybe it's a little bit higher or lower. It doesn't affect the location of the x. Right? So if you have a change in the x, so you have this function. Right? That depends on how high it is. Right? It doesn't affect where it's located. Okay? So if that's the case, and then we can presumably we can directly take this form as the original Gaussian distribution form, right? Taking the original distribution compared with this form, we can say that the targeting product of these two Gaussians, the sigma and the mu, will be quite close to this one. Close to this one, but there's a slight difference with the sigma factor. With a complete proof, next step, we will estimate what's the error between this sigma and mu to the real sigma and mu. Right? This is just a summation of sigma and mu. But from this not so precise, but we can still see the fact is sigma fg squared, it should be smaller than sigma f, and also it should be smaller than sigma g, right? You can see the structure on the right. So we have will x be smaller than xy over x plus y? Yes, it was smaller than x plus y, right? Because both cases x or y they are non-negative, or they're positive. Sigma is positive. So you can see this proof, this part of proof, and there are also a little bit shift about this mu. I have limited time. I only have limited time, only a break for 5 minutes. So I'll try to get the complete proof, but this computation is quite close to what you want to get. Remember this as a conclusion first. So as a product, this sigma fg should be smaller than sigma f and also sigma g. So this one, that's the reason. This is the reason why UKF works, right? Why UKF works? This is why. Okay. This is a quick proof, quick non so precise proof. I try to get a precise version, but you can see from this estimation, the general idea is okay. Let's go back to sharing. So if you know this, if you know about this, and then the next next step is is if we don't know about the map, right? If we don't know about the map, then the problem is a slam problem. Right? It's a slam problem. We can use some internal representation. For example, the position of landmarks, define this as a map. And also there are other internal representation like the camera parameter, etc. We assume that robot's uncertainty at the starting position is 0, and this is a fair assumption, right? So that means in this room, consider this is environment. Probably this is a room, and ABC, three feature points. You don't know where they are, right? Just objectively they are there. You don't know where exactly they are, and you don't know where is the robot location as well. I don't want to measure the shape of the room, right? This is not something you care, right? You only care about where can I find the landmarkers, where are ABCs, where are these three feature points. So when you turn on the robot, powered on, and you can assume that the current robot position is what? It's if this is a localization in 2D, it should be at x, y, theta, right? This is how we represent the location. We can assume that this should be 0, 0, and 0. The variance matrix over x, y, z is all 0. Right? It's all 0. So you don't have any uncertainty. Okay, this is a fair assumption because you just turn on the robots, right? So this position is 0, 0, 0. You don't have any uncertainty. Okay. And then the robots use the camera to observe the environment, and then the camera sees the feature A. Then on every frame of the image, we want to predict how the robot has moved and do the measurement, right? If the robot didn't move and already start taking the measurement, it's also fine, right? I just turn on the robot with a 0 uncertainty in location from the camera or some LiDAR. Maybe the camera is a stereo vision camera or whatever. It's a trivial about the setup. And we can have observation of the feature. We can have observation feature. So here you can see, starting from the center of the sensor or the robot, so the feature, that's the way how you observe the environment, right? So typically you have higher uncertainty along the radial distance, right? Okay, along this observation direction. On this direction, you have higher uncertainty. This is normal because most of the sensors, they are bearing sensors, especially for cameras, right? If something is closer to you, then you have a smaller variance. Something is a little bit further, you have a greater variance, greater uncertainty. But anyway, this uncertainty should grow along the direction, right? Because if you have the objects move perpendicular to this frustum, to this observation direction, quite easy to tell, right? So you just have different pixel level difference, right? This pixel level difference, easily you can tell the variance in the perpendicular direction, right? But the estimation of depth, that's a little bit difficult, right? That's a little bit difficult. The estimation of depth, this is hard. And the worst case is you have some uncertainty measurement probably to the infinity, right? We don't know where it is. We don't know where it is. I just know probably something is there. I don't know about the actual location, right? The worst case is like that. So anyway, if you have such a sensor, maybe it's a stereo camera or what, you can have observation of A, the uncertainty of A with this shape, Okay. When the robot moves, its pose uncertainty will increase, right? Obeying the robot's motion model. As we mentioned, like a typical differential drive robot. So you have greater uncertainty on the side, right? Greater uncertainty on the side, a smaller uncertainty, so you're more sure about how far you travel. So that's the motion update, right? Motion update. Okay, you have an increased uncertainty. So previously the uncertainty is zero, don't have any eclipse. Now you use a greater eclipse to show the robot position with a higher uncertainty, right? The robot probably is here. There's some low likelihood, right? Low possibility. Okay. And then the robot sees two what? Sees two features. Similar to the observation of A, now you start to have some understanding of the position of B and C. But one thing is different than that for A. What is different? What is different? You are more certain or more uncertain about the position of B and C. So estimation is getting better or getting worse. Are you certain about the position of B and C? More certain or less certain? Comparing to the estimation of A. Getting what? Getting uncertain, right? Getting uncertain. Why that? Because when you're at the initial position, you know exactly where you are, right? So you're at 0, 0, 0, right? That's where you are. But now you have a robot position, you don't know where it is, right? You don't know where it is. It's just a two-dimensional Gaussian. It's a 2D Gaussian with large enough uncertainty, right? Large enough uncertainty. Then what? Then your observation to B and C will lead to higher uncertainty in the the position estimation of the markers, right? So BC, you see the uncertainty also grow along the direction of the observation direction, right? And but the radius of this uncertainty grows significantly due to the uncertainty of the robot. Okay. Okay, this is clear. And then you keep moving, then this uncertainty keep growing, right? Keep growing. But suddenly you see the A. You see the A, then what will happen? You see A. What? If you want to give a new estimation, if you want to provide a new estimation on the position of A, what probability you will provide? Maybe this is A is somewhere here, right? This red eclipse. Okay, based on my current location, I have even bigger uncertainty about the position of A. Right? This is natural. But what is unnatural is this is A, right? You have seen A before. This is called loop closure detection. Right? We detect the loop closure. That means we move the one circle around, we go out for a round and come back to some place I already visited. We detect loop closure. Right? With this loop closure, we know that's exactly your point A. Then you can do what? You can use the previous, this blue one, this blue uncertainty as a prior. And this red updated uncertainty as what? As a likelihood, right? As a likelihood. Then you can do what? You can do the product, right? once you make a product of these two eclipse, so you have a Gaussian times a Gaussian, you get what? You get a smaller Gaussian. You get a Gaussian with a smaller variance. So the red one multiply with the blue one, pixel-wise multiplication, we will do have a smaller variance. So smaller variance in A. So you get more certain about the position of A. Meanwhile, you will get a better estimation on the road poles. This guy, right? This uncertainty will also drop because you have seen A before. That will also drop. Also, the estimation of B and C, right? It will also drop. Okay, all the uncertainty will shrink. So does the uncertainty of the map, right? So that's the effect. That's the effect of the SLAM system in terms of the Bayesian progress. In terms of this progress, you see, you start to have uncertainty, and finally this uncertainty will shrink, will drop, according to this loop program. Okay, so that's what happened in 2D with the unknown map. Unknown map. So today we discussed several examples. Right, the first example is you have a 1D case with a known map. Right, then you have a 2D case with a known map. Now you have a 2D case with unknown map. Right, 2D case with the unknown map. And for the 3D case, etc., just the same idea, right? Same idea. This is what this is called probabilistic SLAM. Probabilistic mapping or SLAM, right? Probabilistic SLAM. Many new or recent progress in SLAM, people turn to use the photograph. Right? We can also quickly introduce the photograph. Not now, but later. But both ways, we can formulate them in the format of the Bayesian progress. Okay, one or sometimes we call this is the filter based. Right? Why is the filter based? Because this progress can also be explained as a EKF, right? It's the extended common filter. So this is called filter based mapping or filter based SLAM. And the postgraph is more like optimization based, right? You have optimization over the graph. So, okay. Any questions? If not the case, we can go on with the two updates, right? We mentioned that there is a action update. Also, there is another name is another side of the story is the perception update. So action update is to estimate its position through the proprioceptive sensors, and sometimes we also call that egoceptive. Right? Egoceptive means ego means yourself, right? Egoceptive sensor. So during this step, it's like the robots move around, right? I don't see any have any sensor feedback. In this case, starting from a very short position, and you will increase you'll grow this uncertainty, right? As long as you move, you are accumulating errors. So you have a higher uncertainty, and then the peak will drop, right? So that's called action update, right? Action update. A second update is called perception, or sometimes a measurement update or sensor or observation. So whatever words you want, that is you use. So it's just a perception. For the perception updates, you make an observation using extraceptive sensor like LiDAR, camera, ultrasonic, etc. And then you correct the position by the opportunity combining the belief before the observation with the probability of making exactly that observation. Okay, it seems complex, but what we really want to say is you have this dash prior, right? This is prior, and this is a likelihood. You multiply this prior with the likelihood, you will get the posterior. You will get this posterior. Okay, so that's the two updates. You can separate the modeling process into the two steps. Then we can look at the ingredients, right? A probabilistic approach to this mobile robot localization is a method able to compute the belief, right? The probability distribution during each action of certain state. The ingredients, that means what do you use to compute all these probability? You need the initial probability distribution. Usually this is uniform, right? Uniform. And you need a model, a statistical error model for the real odometer, right? The egoceptive sensor. And you also need the model for the extraceptive sensor. Okay, sometimes this egoceptive sensor can be a real encoder, can be an IMU, etc. Right? Something can estimate the motion of itself. And then this lasers on a camera, so that's used to perceive the environment. And number 4 is the map. So if you know the map as a prior, it's a localization. Right? If you don't know the map, then it's a SLAM. It's a SLAM. Okay, that's the 4 ingredients. If we look in detail about these 4 ingredients, then what do we see? We see that the error model, if you move your, let's say, real robot, differential drive robot, to some position, actually the oscillity looks like this. You can see it's not a Gaussian. It's not Gaussian, right? It's a moon shape, right? For the statistical error of the camera or LiDAR or laser sensor, you see this is a statistic or characteristic of ultrasonic. This is LiDAR. It may look like a Gaussian. This shape looks like a Gaussian, but there will be some peaks. Sometimes you have the peaks, depending on the characteristic of the sensor. You may double counting the reflected signal. Right? So it's overshooting the maximal. Okay. So typically, this is close to a Gaussian, but it's not a Gaussian. Statistically, probably you can say this is probably a Gaussian. But in practice, we use an assumption, right? Both of them should be a Gaussian, right? Both of them should be a Gaussian. Not saying this is not a Gaussian, but we say, okay, you should be a Gaussian. Both cases should be a Gaussian. Will that cause problem? It may cause problem, right? It might cause problem. So that's why for the research of SLAM, people try to specify these distributions, right? But if they are not a Gaussian, and then the common filter cannot be applied, right? currently cannot provide. Why that? Because you multiply the prior with the likelihood. You cannot guarantee you have a converged covariance matrix. That's why practically you assume all these should be Gaussian, but you should know that they are not Gaussian. Right? They're not Gaussian. So there's still some space for you to optimize the work in the STEM domain. For example, if you have such a structure, how can you better approximate a Gaussian? You can use a UKF, right? You can use UKF, for example, right? Or the sometimes you use a different kind of the optimization algorithm. Or sometimes, see, if you localize in 1D, for Gaussian distribution, it's defined from the infinity, minus infinity to infinity. But the actual uncertainty is bounded, right? You cannot go beyond, for example, the walls. Right? You have some defined area. Right? Even that is it's not a Gaussian property, right? You have a bounded regions. So sometimes you have a T distribution. With a T distribution to replace the Gaussian, but the deduction or the equation will be much complex. So all these are normal. Right? All these are normal. Next time we quickly finish all of these equation parts and go through the filter based method. Now you should see. Okay, let's answer the questions. This is for next week. Sorry. I don't have further question for this week. In the chat window, can we assume it's a Gaussian with a larger variance such that we can know low bound of the estimation error? Well, I think I just explained this issue, right? No matter how, if it's a Gaussian distribution, you are defined from the infinity, minus infinity to positive infinity. So that nothing to do with the lower bound of this estimation error, because even you say if it's beyond lower than a certain threshold of the probability, I consider there's a zero probability. Well, you can assume that. You can assume that. The truth is, you still have the chance, right? You have possibilities. It's not a zero possibility, right? Even you have 10 to the power 100 possibility, it's still something greater than zero. So generally, this kind of assumption cannot help. Right? Cannot help. So you can assume it's a larger variance or smaller variance. Typically, it doesn't matter, right? Typically, it doesn't matter because you can also consider that as the output of localization will be a distribution, right? Will be a distribution. So, but the actual need from application, for example, this is a distribution. Probably in this case, I won't trust any of these peak. I don't trust any of this peak, right? And if you have a distribution like very smooth, then if I ask for a point estimation, the best guess is still here, right? The best guess is still here. It doesn't matter if you have a smaller variance, let's say a much higher certainty. Okay, the red case, again, you will have the estimation to be here. So it doesn't matter, right? The actual numerical value of this